here's what I want you to recognize. First of all, there's a picture here that will really help us understand what's going on. And I can't draw it to scale for reasons that'll be obvious, but I'm going to draw it at least somewhat to scale. So here's the Earth, right here. And here is the Hubble Space Telescope, right here. The Earth has a radius of about 6.4 times 10 to the 6th. So when I write exponential numbers, I write e and then the power of 10. That's how it'll show up most likely on your calculator or computer. So 6.4 e6 is the same as 6.38 times 10 to the 6th. And then the distance from the surface of the Earth to the Hubble Space Telescope is about 600,000 kilometers. Or sorry, 600,000 meters. So, this distance is much smaller than the radius of the Earth. I can't draw it to scale though, but you can see like this distance is pretty small. The distance to the center of the Earth is pretty large. When we're dealing with orbital motion, the r that matters is the distance from the center of one object to the center of the other. So this is our r, and it would be the combination of these two things. This is 6 times 10 to the 5th power, 1, 2, 3, 4, 5, plus 6.4 times 10 to the 6th power is going to be about 7 times 10 to the 6th power. And you can use your calculator to verify that. Don't trust me, because I'm notoriously bad at doing arithmetic in my head, especially if there's exponents.
You're really, really close.
What was it?
It's 6,976,000.
Oh yeah, because I rounded.
Yes.
Yeah, so it's close to 7,000.
You're close, yeah.
So we've got an R. So what could we find here? Well, we don't have either of these things, so this isn't useful. We don't know the mass of the Hubble Space Telescope, so we can't find this directly. We don't know V. We can't use any of these things. But what we do know is that the centripetal force that keeps the Hubble Space Telescope changing direction at the right rate has to be equal to the gravitational force between the Hubble Space Telescope and the Earth. So mv squared over r has to be equal to big G, big M, little m over r squared, where big M is the mass of the Earth, little m is the mass of the Hubble Space Telescope. This shows up on both sides of our equation. This shows up on both sides of our equation. Over here it's twice. Over here it's just once. That means that the orbital speed of the Hubble Space Telescope should be the square root of g times large M divided by r. And I'm not going to put the numbers in, but if you're not used to using a calculator to use these kinds of numbers, expect to get the wrong answer. And it doesn't matter. Even on the AP test, they're not likely to give you a problem where your inability to put in this number on your calculator or 6.7 times 10 to the negative 11th on your calculator, that's not going to be the deal breaker, right? They're going to ask you conceptual things. They're going to ask you something like, if the Hubble Space Telescope were to move further away from the Earth, would its orbital velocity need to increase or decrease? Explain. Something along those lines. Okay, so we could find this, right? Not super tricky to figure that out. Okay, so the next one that I want to look at is this. And this one is way trickier. And it starts the same way. I'm going to help by drawing you the picture, because I think this isn't necessarily an intuitive picture, but what we've got is the moon. So it's our moon. It's right here. And then we've got an astronaut in a spaceship. So here's the astronaut in the spaceship. And let's make this box the spaceship. Okay, so the reasons for that will become clear momentarily. We know the distance from center to center. We're given that it's 4,200,000 meters 4.2 times 10 to the 6th meters away from the center. So center to center, we've got that number. We know the mass of the Earth's moon. And what do we know about the vehicle? Well, let's just look at part A. It's moving at a constant velocity. What does that mean? Do we know what direction it's going? No. Do we know that it's actually moving at all? No. All we know is that it's not accelerating. What's the simplest case of constant velocity with no acceleration? Yeah, 0. So let's have this be motionless, and the acceleration is 0. If we had a spaceship, here's a spaceship right here, this is my spaceship EGOT, and a planet, and we just, like, if I was big enough to do this, I like put the moon right here, and then I put my spaceship right here, and then I let go. The moon is the real moon. The spaceship is a real spaceship. What's gonna happen?
Spaceship go.
Right? And actually, we know since the gravitational forces affecting both of these objects, the moon is gonna also accelerate toward the spaceship, but not in a way that we ever would be able to measure.
It's trivial.
Okay? So it is trivial. So what does that mean if the acceleration is 0? How do you achieve 0 acceleration? We know that if we just put them there, they accelerate toward each other. What's the only way to get 0 acceleration here?
Oh.
How do you get 0 acceleration? If you were in a rowboat on a river and you wanted to not accelerate or not move relative to the shore, what would you have to do? You gotta row. You have to exert force just to stay still. If not exerting a force would mean you accelerated in this direction, that must mean there's a net force in this direction. If you don't want to have any acceleration, you have to exert an equal and opposite force in this direction. Now we can draw our astronaut, because our astronaut is going to be standing like this. How do we know? Because the ship is going to be pushing this way. It's going to be pushing, the rockets are going to push on the ship is going to push on the astronaut, because if there's no force on the astronaut from the ship, then the astronaut is going to accelerate toward the moon. There can't be any motion here, which means there must be a force in this direction on the ship and everything in the ship from the engines, okay? So, and then the last thing that I'm going to remind you of is we talked about apparent weight. And that was when we talked about, we did this ages ago, we had those force sensors with the L brackets on them, and we were tilting the force sensors, and we were reading what the force sensor said. And what we determined was that what the force sensor told you was the magnitude of the normal force that was like perpendicular to the force sensor, and that was what we call apparent weight. So when you have a person standing on a scale, then the number on the scale is the person's apparent weight. That's how heavy they feel. If I stand on a scale, motionless on the surface of the planet, there's one downward force from gravity, that's my weight. There's one upward force from the scale that will be equal and opposite to my weight, and that's what I feel. You can all feel it right now. Your feet and your bottoms are being pushed upward by whatever they're in contact with. That is how you feel your weight. You don't feel a downward force. You cannot feel a pull from the earth. You feel a push from what's preventing you from accelerating downward. If you're in free fall, you do not feel a pull. You feel weightless. Why? Because if you were in free fall, this scale would read 0 newtons. It wouldn't be pushing up on you at all. Your apparent weight would be 0. You would feel like you were weightless. You're not. This astronaut has weight. That weight is determined by the magnitude of the force that the moon is pulling on that astronaut with. But what the astronaut feels is the floor of the spacecraft pushing in this direction. All right? So with all of this information, let's see what you can do about part A, where you've got no acceleration. This is the setup. What is the apparent weight that this astronaut is going to feel? In other words, if we were to put a scale right here, what would that scale say? What would the scale say if that person were standing on it on the floor of the spacecraft? And it's weird because it's angled like this, but you know, orient the other way if that's easier for you. There you go. Right, let's see what you can do.
Sorry. U weighs 140